Last video I talked about slice rank and also about the cap set problem. I introduced slice rank in order to, which was going to be part of the solution to the cap set problem. And now I want to show how that works. So also, this is, as I said, part of the course where I talk about the polynomial method, and polynomials have so far not made an appearance, but they're just about to. So let's just have a quick reminder of what the cap set problem is. It's to prove the following theorem with a good bound. So the theorem says for every delta greater than 0, there exists an n such that for every subset A of f3 to the n, if the size of A is at least delta times 3 to the n, then A contains various different ways of putting it, but the most convenient one is going to be x, y, and z, not all equal, such that x plus y plus z equals 0. Now, the key point here is going to be that we are going to be able to, so here comes the proof. It's going to be that there is a polynomial that's going to be able to express this condition, or it's going to be able to we're going to be able to exploit this if A is a set that does not have this condition. So in order to do the proof, let A be a subset of f3 to the n with no x, y, z distinct. Actually, I'm going to put the word in because it's actually very important here. Distinct, such that x plus y plus z equals 0. Now, what I want to do here is obtain a very efficient way of writing down a function that's 0 when x, y, and z are not all equal, and non-zero when x, y, and z are when they are equal. Sorry, I think I said that wrong. So it's 0 when they're not all equal, and 1, or non-zero at any rate, when they are all equal. And the way we're going to do it is to say that note that if x, y, and z belong to A, so we just make the following observation: are not all equal. Sorry, that's not what I'm going to say the contrapositive of what I'm about to say. So if they satisfy x plus y plus z equals 0, then they are all equal. And that's going to be something that we can exploit by defining a polynomial. So we'll consider the following polynomial. It's going to be an x, y, and z. So I'll write it as f x, y, z equals the product I equals 1 to n of xi plus yi plus zi. I'm going to put it this way around. So 1 minus that squared. So let's look at a particular I. If xi plus yi plus zi is 0, then this will be 0 and we just get 1. If xi plus yi plus zi is not 0, then it's either 1 or 2, and 1 squared is 1 and 2 squared is 1, and then we'll get 0. So the right-hand side here, so the right-hand side is 1 if all these things here are equal to 0, if x plus y plus z equals 0, and 0 otherwise, because if x plus y plus z is not 0, then at least one coordinate is not 0, and then we get at least one factor of this big product that's 0, which kills the whole product. So naught otherwise. So if x, y, z, or let's just say, so the restriction of f to a cross a cross a, so in other words, if x, y, and z all belong to a, agrees with the function that's 1 if x equals y equals z, and naught otherwise. So it has, by the slice rank lemma that we proved in the previous video, it has slice rank size of A. And now what we're going to do is obtain an upper bound for the slice rank, which will then show that we get an upper bound for A. And we've already written a polynomial here, and the upper bound is just, we're going to obtain an upper bound by showing that this polynomial can be written in an efficient way as a sum of products of functions of one variable and functions of two variables. So what can we say about the polynomial? So f has degree, so total degree. So each bracket here is a quadratic, and we're multiplying n of them together. So 2n, and it's in the 3n variables x1 up to xn, y1 up to yn, and z1 up to zn. So it's a pretty terrifying polynomial, degree 2n in 3n variables. It also has degree at most 2 in any one variable. So it works out as and we can write it as a linear combination it's an F3 linear combination of monomials, so that will be the form some kind of product. I'll write it out once, sort of y1 to the b1, up to yn to the bn, z1 to the c1, up to zn to the cn. So in each case we've got, so what can we say about these monomials? So there'll be some coefficient in front, so we can say that a1 plus an plus b1 plus bn plus c1 plus cn is less than or equal to 2n for each of these monomials. Each ai, bi, and ci belong to 0, 1, or 2. And now, if we look at this, we see that at least one of these sums, by just averaging, is at most 2n over 3. So let's partition these terms into 3 sets, such that in the first set we have monomials of degree less than or equal to 2n over 3 in x1 up to xn. And in the second set, it's the same but with y1 up to yn, and in the third set, it's the same but with z1 up to zn. So roughly what we do is we take each term, we look to see which of the sums a1 up to an, b1 up to bn, and c1 up to cn is the smallest, and then we stick it into the sort of x collection if the a1s are the smallest, the a's are the smallest, and the a sum, whatever, and the y collection if the b's are the smallest, and the z collection if the c's are the smallest. And if there's not a unique smallest, it doesn't matter, we just choose one of the smallest ones. Now, let's just see what we're going to do with these. So let's focus on the ones where we have monomials of degree at most 2n over 3 and x1 up to xn. So let's just pick one such. So each one is going to have a term x1 to the a1 up to xn to the an. With a1 plus an less than or equal to 2n over 3. And it'll be some other monomial in the y1 up to yn and z1 up to zn, multiplied by some coefficient. So if we just add together all the terms that involve this particular set of powers for x1 up to xn, we'll get that times some function which I could call, let's say, v of v a1 up to an of y and z. So just to say what I've done here, I've picked out a particular choice of a1 up to an for my powers of x1 up to xn. Because it's in the sort of x collection, I know that a1 up to an, the sum is at most 2n over 3. And then I've taken all the bits of all the sort of monomials in y1 up to yn and z1 up to zn that go with this particular power of x, or set of powers for x1 up to xn, and I've just added them all together with their coefficients and got some function in just y and z. And I do that for every single monomial like this, and that means that I've written all the things in the x collection as a sum of a function of x times a function of y and z. And how many such, so I've got a sum of those things, and how many of them have I got? I've got the number of monomials in x1 up to xn, or the number of choices for a1 up to an. In other words, a number of ways of choosing a1 up to an in 0, 1, 2, with sum at most 2n over 3. So what I'm going to be able to say here is let m be the number of naught, 1, 2 sequences that add up to at most, sorry, of length n, that add up to at most 2n over 3. And I've shown that the contribution from the x terms will contribute at most m to the slice rank. Then by symmetry, that's the same for the y terms and the z terms. So then the slice rank of f is less than or equal to 3m. Takes a little bit of getting used to that argument. I'm going to repeat it once more. So I've, out of all these monomials which have coefficients lambda blah blah blah, a1 up to an, b1 up to bn, c1 up to cn, First of all, I select the ones where a1 up to an has the smallest sum, and I partition those according to whatever a1 up to an is, and then I put in all the possible monomials in y1 up to yn and z1 up to zn with their coefficients that go with that particular a1 up to an. And that gives me some function va1 up to an of yz. And that in total gives me a function of x times a function of yz. And I do that for all the possibilities for a1 up to an, which then contributes capital M to, I mean, the number of functions that I've taken here is capital M. And then I do the same for the ones where b1 up to bn is smallest and c1 up to cn is smallest. And I get another m functions and another m functions. And the total number of functions I've got, which are products of functions of one variable and functions of two variables, is at most 3m. So the slice rank of f is at most 3m. And so that tells us that the size of A is less than or equal to 3m. So all we have to do now is establish that m is exponentially smaller. So this bit is not a problem, because if we look at this, let's just pick a random. Actually, the easiest way of doing this is to say so the number of sequences in 0, 1, 2 to the n that add up to less than or equal to 2n over 3 is the same as the number of sequences in -1, 0, 1 to the n. I'm just going to take 1 minus the sequence here. So 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 2 is -1, that add up to at least n over 3. So we can say let, this is not going to give the best bound possible, but I don't mind too much about that. So let x1 up to xn be independent random variables chosen uniformly from -1, 0, 1. Then average of sum of xi equals 0, and the probability that sum of xi is greater than or equal to n over 3. We did this in the section on estimating things like binomial coefficients. So these are random variables that have modulus at most 1 all the time. They're independent and they average 0. So the probability that their sum is at least n over 3 is less than or equal to e to the minus it's c squared n over 2, where c is now 1 over 3. So n over 18. If I remember rightly, but I think we can probably do better than that, even using the bound that I did earlier in the course. We can certainly do better than that in general if you work out the exact probability here, or not the exact probability. What you can get what the right exponent is. That's known. But at any rate, it's exponentially small, and I'm using the probability that it's at least alpha n is at most e to the minus some constant alpha squared n. I've just forgotten what this constant is, but I think it's a half is certainly safe, but I think it might be able to do as well as 1 or maybe even 2. But anyway, I'm going to play it safe and say something that I know is definitely true here. The point is that this probability is exponentially small, so that tells us that a is less than or equal to 3 to the n times e to the minus n over 18, or possibly something a bit better than that, but that's already exponentially small. So smashes the 1 over n to the 1 plus epsilon bound, or 1 plus little c bound, I think I called it earlier on, or in a previous video of Bateman and Katz. So this came as a real surprise when this was done. And here I think it's the most extreme example of what I was saying about the polynomial method being a bit mysterious, because there are a whole lot of other problems that have only been done or had only been done using Fourier analysis type methods, which I've not talked about in this course, but will be certainly talked about in the additive combinatorics course next term. And so people started looking at some of those other results to see whether those also could be done using this extraordinary technique, using slice rank or polynomials and so on and so forth. And it seems that either you run through an argument very similar to this and it all drops out nicely and the ideas carry through quite easily, or you try it and the numbers just don't work out, and then you don't seem to get anything at all. And somehow it's very unlike other techniques I know. So with Fourier analysis, if the first argument you try doesn't work, then you sort of think, well, maybe I'll try and do something a bit cleverer, or I'll try to look for where the weakness is in the argument when I try to do the straightforward approach. And I see, oh yes, well here, that inequality, if this one's sharp, this one won't be sharp, maybe I can exploit that somehow, that type of thing. But with this method, you don't get the feeling of that sort of thing. You don't you feel that you can't sort of exploit its weakness. Either the magic works, the rabbit sort of pops out of the hat, or it doesn't. And so there are, to give you an example of a question that people would very much like to be able to solve, supposing we take a subset A of f3 to the n squared, it's known that you can, if it's dense, so if n is large enough, and we've got some delta greater than 0, we can find a triple of the form xy plus d, and x plus d y, where d is non-zero, that all live in A. But the bound that comes out of that is not terribly good. So the question then is, natural question is, can we use this slice rank approach to get a much better bound? And if you try it, you find that you can sort of run the argument, but when you get to the stage of what m is, you find that you've got a certain number of sequences that's just not small enough to tell you anything, non-trivial. So that sort of the number that you want just doesn't appear. And because you've produced this slice rank decomposition in a very specific way, there doesn't seem to be a way of sort of saying, well, maybe because of the particular way that this polynomial, there doesn't seem to be an obvious way of exploiting it to show that it can in fact be written more efficiently than this method would suggest. And in fact, I think it's very likely that it can't, the polynomial that you naturally write down when you start thinking about this problem. So it's a strange method, but it's had some extraordinary successes. And I will, with that little remark, I will stop this video, and we'll be moving on to a new subsection of the course, although polynomials will make an appearance towards the end as well, in a slightly different style of argument.